In lecture 74, we have introduced the parameter about resonance, that is, quality factor, which is used to describe the quality of the resonance. Similarly, about the mutual inductance, we have also introduced a factor to describe how close the two coils are coupled. The factor is called the coupling factor. Its definition is that the ratio of the mutual inductance and the square root of the product of two self-inductances. According to the definition of self-inductance and the mutual inductance on the right side, substituted these parameters into the definition formula, we can find that the square of the mutual inductance is no greater than the product of self-inductances. Hence, the coupling factor must be less than or equal to 1. As we said in the introduction part, mutual inductance is a natural phenomenon. Sometimes we need to use it, and sometimes we need to restrain it. In order to make full use of the mutual inductance, sometimes it needs to be a kind of extreme situation, that is unity coupling. In this case, K equals 1, that is M squared equals L1 times L2. So how do we constitute unity coupling by using two coils? You might as well think about it. You see, the red and black lines represent two coils respectively. If we wrap these two coils as a solenoid coil in parallel, then almost all of the magnetic flux produced by the two coils is linkage. So their coupling factor will be very high. But sometimes we need to restrain the mutual inductance and require very low coupling factor. You think about it too? How do we make coupling factor of two coils close to 0? Look, if the direction of the magnetic field generated by the two coils are vertical, then the magnetic flux generated by a coil would have no linkage with another coil, so the coupling factor is 0. At the end of this lecture, we will discuss mutual voltage. The analysis way is the same as the self-inductance. According to Ampere circuit law, current and magnetic flux are with right-hand relation. That is to say, after given the direction of the current on the left, we assume that all of the magnetic flux flows in the box, then the magnetic flux flows clockwise. According to Faraday law, magnetic flux and the electromotive force are also with right-hand relation, so the electromotive force is negative above and positive below. Under such reference directions, we have E21 equals minus d psi 21 over dt. If the mutual inductance is a constant value, then it equals to minus M times di1 over dt. Because the mutual inductance involves two coils, so we usually draw it as a two-port network. It means that we follow the definition of the reference directions of the ports, voltages, and currents introduced in lecture 27. The voltage is positive up and negative below on the right port. In this case, we know that U21 equals minus E21. That is, U21 equals M times di1 over dt. So far, it looks almost identical to the previous derivation of the inductance, but if we change the winding direction of the coil on the right side, you see? Similarly, according to the right-hand rule, the current generates the magnetic flux with clockwise direction. According to the definition of the reference directions in Faraday's law, we need to have a electromotive force with the direction of the positive above and negative below, so as to get E21 equals minus d psi 21 over dt equals minus m di1 over dt, but the voltage on the right side is also need to be positive above and negative below. Hence, U21 equals E21 equals minus m di1 over dt. It has a little trouble in the derivation of the relationship between the inductor's current and voltage. Just now, we get a very important conclusion. That is, for a one-port inductor, if we define the associated reference direction for the current and voltage, then it must have U equals L di over dt. For the two-port network of mutual inductance, so far we need to draw the winding directions of the two coils to determine the sign relationship between the port's voltage and the current. It is troublesome in practice. We will give a splendid answer about this problem in lecture 78. Well, that's the end of this lecture.